All right, so those of you that are picking up with this lesson at home, Mitch is fixing to help us with number 4. These are our warm-up questions, kind of getting the ball rolling for our lesson on logarithms. Mitch, what did you do to not number 1, number 4?
I knew what it was. Because 3 to the power of 3 is 27, but I checked my answer with log base 3 of 27.
Oh, okay. So I want us to not necessarily use logs, but I want us to make the base the same. So did you?
No.
Hey, pick your head up and mind your own business. And that's rather hypocritical to someone who has their shirt untucked. I shouldn't see your lower back. Back to the point at hand. 27, I think, as Mitch was saying, is 3 to the power of 3, and we want to make the base the same. And therefore, x equals 3. So if I can make the base the same, so 3 to the x equals 3 to the 3, then I can equate those exponents. And I can say, oh, okay, well, x equals 3. We learned about that last week. And we can similarly attack number 5. Now, how do I make 1/8 2 to a power? Mitchell? Okay, so 2 to the x equals 2 to the what? Negative third. And therefore, x equals negative 3. Right? Because 1/8, ready, is 2 to the negative third power. Now, number 6 is a check to see if you've got that definition memorized. Let's see if Alfredo does. Alfredo, what would make 5 to a power? What power would make it equal 1? What do you think, Alfredo? Very good, 0. By definition, 5 to the 0th power equals 1. So here, x equals 0. And there are our 3 answers for those last 3 warm-up questions. All right, so anything else you needed to ask about the warm-ups before we jump into logs? Mr. Green? All right, so we got to make sure, this is important for this lesson, we got to make sure we're good on our exponent rules. If I've got a to the negative n, that's 1 over a to the positive n, right? So in our example, if I wanted to work backwards, if I've got 1 over 8, that's the same thing as 1 over 2 to the third, which means that's 2 to the negative third. Okay, so 8 being 2 to the third, that's first key fact to have memorized. And then say, ooh, he's in the bottom, I can move him to the top and make his exponent negative. And there we go. Want to make the base same. Today we're going to discover, well, what in tarnation do I do? Here's an example of a nice equation. What do I do if it's not so nice? What if I had something like 3 to the x equals 5? That's where I have to use our logarithms. And I'm going to teach about logs, teach you some of the basics. It's not bad at all once you kind of get used to it. So first and foremost, some definitions. I'm sorry, Ken. What was that? Yes. He took a bit of a turnabout there. All right. So a logarithm is an exponent. That might be a true or false question on the exam. A logarithm is an exponent. It literally is an exponent. So when I ask you a question like in the previous page where it was, 3 to the x equals 5, what is x? It involved solving for that unknown exponent involves a logarithm. It is the inverse of our exponential function. We've talked before here on the sideboard. I'll show you again where we've said exponential growth goes up and to the right. The logarithm similarly goes that way. Exponential growth has a horizontal asymptote at 0. The logarithm has a vertical asymptote at 0. So if this is y equals b to the x, here we have y equals log base b of x. These two functions are inverses. If I have a point right here, we'll call this point x1. Now that's perhaps confusing. Let's not use x and y. Let's see, here we'll do S and M for my initials. Then what point will we also have on the log function? M, S. There we go, just making up 2 letters that aren't already being used for something in this context. So those 2 functions are inverses. Exponential form obviously is where you've got an exponents. Logarithmic form is where you're going to have logarithms. A log has two parts to it. A log has two parts to it. So we have what's called the base of the log, which describes the kind of logarithm that you're dealing with. And then you have the argument, what you are operating upon, what you're taking the log of. Okay? So much like you have a square root, square describes the kind of root, and what you're taking the square root of is the argument. A logarithm has a base, and what you're taking the log of. Very similarly posed there. Okay? So logarithm, base, argument. There's a couple of special types of logs that you may have come across. You'll certainly see it as I open up my calculator. You'll certainly see that there's two log buttons on every calculator. There's log, which is the common log, and there's ln, which is called the natural log. And you can think of maybe someone in a different language, maybe like the French language, logarithm natural. You can kind of put the adjective after the noun. Right? So there's log and there's ln. And those two buttons right there on my calculator, log and ln, those are our most often used logarithms. One of them's got a base of 10, and one of them's got a base of e, which is whose number? Euler's number, Mitchell. All right. Now in calculus, I'll go ahead and tell you, a vast majority of the logarithms that you deal with in calculus will be natural logs. They'll be based on Euler's number and the natural base. And so get used to dealing with that. Ln means natural log, and that's the inverse of the exponential function where the base is Euler's number. Okay. The common logarithm, because we operate in a base 10 society, you know, we count by tens. We got powers of 10. And so the common log has an implied base of 10. So Freddie, as you pick up your pencil, if we don't see a base, it's implied to either be 10 for log and e for ln. If you don't see a base, it's implied to be either 10 or e based determined by what letters are used, ln or log. Now, at the bottom of the screen, now this is a lot to take in. We're going to practice using this. But at the bottom of the screen, we've got what's called the change of base formula, which is a really handy dandy formula. I'm just going to highlight maybe the part that I would write down, because there's a lot down there. That's called our change of base formula. Can I zoom in on it for a moment? Make sure everybody can see it real good. So log base y of x, you can split. And the way that I remember this is y is the base. He's living in the basement. He's down and dirty. So when we have him in our change of base formula, he's in the bottom. The y is in the bottom. When you got the argument, he's riding high. He's living up on high on the hog. He's in the penthouse. He's up top, so that x is up top. Okay? So when we're talking about the change of base formula, the x, the argument, is up top, while the base is down in the basement. And the base b is whatever you want within reason. And what do I mean by within reason? Bases have to be greater than 0, not equal to 1. You remember that from our talk about the exponential function. Base has to be greater than 0, not equal to 1, just like with exponents. Since logs are inverses, they have to play all by the same rules. Bless you. So if I wanted a base of 3, and I've got like log base 5 of 8, then I could split it and I could say, oh, well, that's log base 3 of 8 over log base 3 of 5. I could split it that way, make the base whatever I want, as long as that base is not equal to, or greater than 0, not equal to 1. Eli. No, that's an equal sign. And so what that means is that these two are mathematically equivalent. It might be more advantageous to write it with a different base, though, so that I can operate upon it and maybe simplify it a little bit differently. Manipulating algebraic expressions is name of the game for this course, right? So we've got to make sure we're comfy sort of manipulating and rewriting expressions. He's been sitting next to you 7 weeks and just now realized that. Nash. Oh, baby, are we fixing to do some examples? I thought I asked everybody to charge their calculators on Thanksgiving.
Yeah.
What?
I don't know how to take.
There's this great website I need to familiarize you with. It's called Amazon. Yes.
What did they say?
I thought you were gonna say Desmos, because Desmos now will give you a logarithmic function given points.
What?
Amazon only sells books.
What? Ah.
Kenneth. Everybody boo Kenneth.
I need one too.
There's Morgan.
I need one.
Kenneth, I got terrible news.
Yeah.
Somebody has stolen my other one.
Oh, Nicholas.
It's like Nicholas had stolen it. Ah, I
He
do.
borrowed without.
Gotta put it back at the end.
He did.
Now, I highly recommend, all jokes aside, I highly recommend that you familiarize yourself with how to use logarithms on your calculator. That's part of what we're going to practice today. We're going to do it without a calculator, doing it by hand, as well as with a calculator.
Do you know that Desmos will give you a function given?
That's nifty. I did not know that. All right, here's example one. I'm going to put this up at the top of the screen. Give myself a little bit of space here. Here's example one. We're given an equation. Finley, okay, buddy? A little tight. We're given an equation in log form, and we're asked to rewrite it in exponential form. And then conversely, we were given an equation in exponential form, and we're asked to rewrite it in log form. Now, if I look at this, I'm going to just zoom in on this first part right here. If I look at this equation, log base 3 of 27 equals 3. That might seem like well, that's no duh, Coach Morgan, because if I punched in on my calculator, log base 3 of 27, it equals 3. Well, duh, okay, you're just telling me something I already know. But the exercise is, can I write this in exponential form? Now, I'm going to be a little bit weird in how I explain this. I'll be a little bit weird in how I explain this. I'll show you in a minute. I'll show you in a minute. That's definitely a skill we need to talk about. So I'll show you in a minute. It's in the math menu. I think it's down near the bottom. But there's also a shortcut. I'm going to ask you the question, can you see it? Can you see it? You might have actually read that in the previous page, this notion of can you see it? Okay. And actually, I'll zoom in just in general. Here's how this works. My question of can you see it is my shortcut for changing back and forth between log form and exponential form. Start with the base, swoop around to the other side, and finish at the argument. Okay? Now that C is backwards. Maybe he's looking in a mirror or something. I don't know. But can you see it? We start with the base, we go around to the X, and then we come back at the A, and read that with me. B to the X equals A. And that's precisely what we have. B to the X equals A. So the way to change from log form to exponent form, in my mind, the easiest way is to say, can you see it? Can you see it? All right, so let's try that little mnemonic here. Can you see it? What would you say? 3 to the third equals 27. And at that point, we say, oh, well, duh, Coach Morgan, I know 3 to the third equals 27. Yeah, great. We took a nice, easy math equation that was in log form, and now we've written it as a nice, easy equation in exponential form. Ready? Don't. Would you mind going to get some? Miss Gresham has it in the main office. You go in the main office, hang a 180, and hers is the first desk. All right. Now, 6 to the 2 equals 36. Christian's like, duh, I've known that for years, Coach Morgan. Okay, let's change it into log form. And where do we start again? Start with the base. Can you see it? So we got log base 6 of 36 equals 2. And a log, true or false? A log is an exponent. True statement. Exam. A log is an exponent. So log, right here, this log equals what? The exponent. It equaled 2, which was our exponent. So change back and forth between logs and exponents. Shall you try one on your own?
Shall I?
All right, let's do this. Log base 3 of 81 equals x. Let's solve for x without a calculator by turning this into exponential form. Log base 3 of 81 equals x. Can you see it, Phil? Start with the what? 3 to the power of equals. Very nice. So 3 to the x equals 81. And now this becomes a problem just like 4, 5, and 6 on the warm-ups. Can you make the base the same, Franklin? What's 81 the same thing as? Say that second thing. Second. Somebody said 3 to the 4.
It's 3 to 4.
Was that not Franklin that said it? Because I know I was talking to Franklin. That was Kenneth who answered for somebody else?
No, that was Phil. That was Phil.
Ooh, y'all be some finger pointers. All right, so 3 to the x equals 3 to the 4th. And hey, I tell you what, Franklin, you can think of 9 squared and then just be like, oh, well, 9 is 3 squared and 3 squared, and so you got 4. And so we would say x equals 4. Do you see how it's easier changing an equation from log form to exponent form and then solving it out? Right? If I can do that, then I probably will be best served by doing that. Let's look at our next examples. Let's try and do similarly without a calculator. And then afterwards, I'll check our answers. We'll show how to do it with a calculator. On A, the implied base is 10. Very good observation, Mitchell. The implied base 10. So that's what we're trying to ask. And Michael Davis, when I don't know what something is in algebra, what can I use for that? I can use a variable. You're killing me, Smalls. All right, let's see here. Sebastian, can you see it? Stephen, 1,000 is 10 to the what? Can we stop answering for other people, for crying out loud? I know y'all are all smart. That's why you're in this class. You don't have to show out. You can let somebody answer their own daggum question. Stephen, 10 to the 3rd, so x therefore equals 3. Now, this is doable because I say without a calculator. This is doable without a calculator because we were able to make the base the same. All right. So how about part B? Suppose I don't know what it is. We'll just say it's equal to y. And Freddie would answer the question, can you see it? One over 49. Beautiful. Now, BJ, 1 over 49 is the same thing as 7 to what power? All right, so y equals -2. And then last but not least, 1/2 to the z equals -8. What do you think, Kenneth? Tell me how, Bob. Tell me how. What is 1/2 as 2 to a particular power? 2 to the what? 1/2 is 2 to the -1st. You answer everybody else's questions. Let's be able to answer your question. I'm gonna ride this pony as far as we can. What's -8 the same thing as? I think my pony has played out. Denegri, help him out. What's 8 the same thing as? Thank you, Mitchell. You didn't whisper? Okay, good. I'm hyper vigilant. I heard somebody say, that's you, BJ? Okay, notice, by the way, though, we got a little problem. We got a little snafu. Does anybody notice the issue here? One side is negative. The other side is not negative. How could a negative thing equal a non-negative thing, guess what? It cannot. So there is no such solution to that type of equation. In other words, this right here is what?
Define.
Undefined. There are some particular restrictions that we have to impose on our logarithm because of the restrictions that were built into the exponential function. Talk to me, Jack, about the domain and the range of this exponential function over here on the left side of my TV. What's the domain of this exponential function? At the arrow's pointing all the way to the left and all the way to the right.
Negative infinity.
Okay, what's the range?
The
How low does it go?
it's negative.
Who's going to help me out? Nash, how low does it go? Good. It's approaching 0, so we'll use a parentheses as opposed to a bracket. You're picking it up. It's all good. And then how high up does it go? All right. Now, the domain and the range, when we come over here, what happens to them? They swap. So, Christian, what's the domain of our log function? From 0 to infinity. In other words, you cannot, Kenneth, you hear me? You cannot take the log of a negative number. I said that very slowly so we could perhaps what? Write it down. You cannot take the log of a negative number. So now that we know that, man, I throw on the brakes for a problem like part C. I go, can't do that. Sorry. It's like taking the square root of a negative number.
Wait, but
You can't take the log of a negative number.
can't you in terms of I though?
Oh, yeah, I'm sure. But we have left the realm of complex numbers. And I don't know how that works, to be honest with you. I hadn't encountered it before taking the
Well,
log
it
of
says it's
negative number.
approximately -3 minus 4.55.
You plug it on the calculator? Yeah. So for our real number system, and I will not be teaching you how to take the logs of negative numbers. This restriction holds. You can't take the log of a negative number in the real number system. Your calculator might give you some funky value. Do not expect to need to know that at all. Nick,
So when you say you're taking a log of number and -8 and 1.
that is the argument. Yes. So the argument for part A was 1,000. The argument of part B was 149, and the argument of C was -8. Those three arguments are what you are taking the log of. And the particular type of log that you are taking is dependent on the base. So this was a common log, this was base 7, this was base 1/2. Now, let's talk turkey on the calculator. If you've got your calculator out, okay, I bet there's a shortcut.
Yeah. Math alpha.
Okay, so there we go. So if you accessed your F2 shortcut menu, so if you hit Alpha Window 5, that's your other shortcut. Really, it doesn't matter to me.
It's easy to just do math alpha math.
Math, alpha, math. Yeah, there you go. Okay. So math, alpha, math gets us to that log base. Now, if you've got an older calculator, you might not have the log-based program. Christian, yours is up in the air. Sometimes it does, sometimes it doesn't. Sweet. So if you got like when I was in school, I had an 83 plus. It did not have this functionality, so I had to use the change of base. So let's practice evaluating these three on here. I'm gonna on part A, it's just common log, so I'll just use that 1,000, and we get our answer of 3. There you go, like we had in blue. On part B, I'm gonna do I like that math alpha math. This out of the way. And then I want my log base to be 7. And the argument to be 1/49. And I get -2 like we got in orange. And then I don't know what I'm going to get here. Mitch, you said you got something.
It's this -3 minus 4.53260142I.
1. And then -8.
Oh, because you don't have it in radian here, whatever mode it is.
Yep.
It's just undefined.
So we're going to say undefined. What do I have it in? I've got it in A plus BI mode.
Well, it gave it to me, and I have it in A+B.
Oh, if it's in radian mode, it matters. So it changes it up.
Yeah,
That's interesting. Very interesting. Some funky number like, okay. Well, hey, let's say it this way. let's say it this way. Can't take the log of a negative number and it's undefined. That's the rule by which we're playing here in high school. Now, suppose that I had my old 83 out and I wanted to run a problem like part B. You okay? Yeah. Suppose I had my old 83 plus out and I wanted to run problem like part B. Okay. Here's what I would do. I would use that change of base formula. You remember what we circled and put stars around? That's what I would use to evaluate a log if I didn't have the log base operation. So what was that one again? What was part B, the example? So log of 1 over 49 divide, oh, actually, instead of doing divide by, let's go and do log of, you also said the base was originally 7. Log of 7. And we get our answer that way. Now that's using the common log. Guess what else log I could use? I could use natural log. I could say the natural log of 1 over 49, close parentheses, and then the natural log of 7, and get that same value.
So what is the graph of log of x over log of x?
It would depend. Oh, that'd be just one horizontal line, log x over itself. So even if you got an older calculator and that calculator right there, that's where you would use your change of base formula to plug that in. All right, so here's it as an exercise. Very quickly, y'all determine what these three are approximately equal to. Practice using your calculator. Practice using your calculator.
Oh, yeah.
And do I need to round?
Yeah. What do I say? Round to the nearest 100th place. Round to the nearest 100th place. Henry. Do you have a calculator today? Participate with the class, please. I know you're locked in for tonight and ready to go, but you got to have a good school day so you can have a good match.
30 pounds hidden.
What are they talking about? 30 pounds. Did you drop 30 pounds? I thought that was illegal for you to drop that much.
Derek Jones.
Coach Harrison got me to. That's funny. I made a goal for myself at the beginning of the school year to drop 30 pounds by June as my goal. I'm working on it. I'm in progress. I'm down 12. So I got 18 to go.
I did that like after solid months.
You had a month to do yours? Oh, that seems sketch. All right, let's go Jack and Blake and Andrew. Jack, Blake, and Andrew. Hundredths. Common log, Blake. Oh, well, let me show you. So it's very easy. You're going to be like, oh, that's so simple. Just hit LN, 7, enter. And then for yours, just hit LOG, 35, enter. You get about 1.54. And Andrew? Does anybody concur with Andrew?
Yeah.
Concur with him? Did we use the log base? We had math, or alpha math, alpha, or whatever it was. All right, superb. Now, perhaps the most important thing that we're going to discuss today is the inverse property of logs. Now, do you remember when we made the turducken?
Yes.
Okay, we went one function into another function, and we said, what is the hallmark of two inverses? What happens when you plug one function into its inverse? What happens? Everything boils down to
One.
See, that was a question on y'all's quiz that you botched. It was a true false question on that 15 question quiz. And it was false because it doesn't boil down to 1, it boils down to x. When you plug a function into its inverse, everything boils down just to plain old x. Okay? Kenneth, I'm assuming you're just charging your calculator and you're not wasting time on the internet. We don't need to be on Blackboard looking at grades. We need to be focused. I prefaced this screen by saying this is the most important thing that we are going to talk about today. It's called the inverse property of logs. What that means is that if I take the log of an exponential and the base is the same, those two operators cancel each other out. If I take the exponential of a log and the base is the same, those two operators cancel each other out. The red and the blue, because they are defined as inverses, they cancel each other out. So now this explains the whole funky sort of can you see it business. Okay. Let me think here. Yeah, we can do it like this. Over here on my side screen, I'm going to show you the alternative. I like the can you see it. I'm going to show you the alternative way as far as like doing an operation to both sides. Michael Esteb, x plus 3 equals 10. What would you do to solve that equation? Subtract 3 because those are inverse operations. Franklin, if I had 2x equals 9, what would you do to both sides?
Make the base the same. No, you couldn't.
My ears are wide open. What would you do? Divide both sides by 2. Because dividing is the inverse of multiplying. Okay, Fredo, if you had, Alfredo, if you had the square root of x equals, I don't know, 7, what would you do to both sides? Square both sides because those are inverse operations. So all of these inverse ops, we've learned over the years that they cancel each other out. So the inverse operation here with logs is exponentiating. So if I were to take, I'll rewrite this equation. Log base 3 of 81 equals x. And I were to raise both sides up as an exponent with the base being the same, right? That's just like where Franklin said divide both sides by 2. Or Fredo said square both sides, right? That's just like where Michael says subtract 3. I'm choosing to do an operation so that it will cancel out, and I'm left with 81 equals 3 to the x, which, by the way, we had right there. I prefer the can you see it approach, but you don't like can you see it? No beef, no problem. Just take an operation on both sides, whether it be exponentiating or whether it be taking the log up. Okay, I'll show you what that looks like here. Good save. Okay. 10 to the power of common log of 56. Kenneth, what's the implied base of that common log? And since those bases are the same, and I'm taking 10 to the power of a log base 10, they cancel each other out, and it equals what?
56.
It equals 56. Okay. Now, what's the understood base class for the natural log?
E.
E. So e to the log base e cancels out. That's 6. Again, e to the log base e, that cancels out. That's 2. Ends up equaling 12 per our definition of inverse functions. Because logs are inverses of exponents. Finley, your shirt tail came out again. Okay. We rocking, we rolling? Am I going a little too fast or is this okay? It's all right? Can you go back? And again, we did this without a calculator. Being able to plug it in on my calculator to check is smart, right? So I could go e to the natural log of 6, and I get my 6 just like that, just like we showed there. So like checking yourself on the calculator is not a bad idea. Now, here we go. Here's an equation I'd like to solve. Now, I'm a can you see it guy, right? But suppose I don't want to do the can you see it. What could you do to both sides? Raise it up as the power of 4. Whatever you do on the left, you got to do on the right. So if I wanted to make the left side an exponent for 4, then I have to make the right side an exponent for 4. Okay? Now these two cancel each other out, and I've got 16 to the x equals 4 to the 10. Now, ask me if I know what 4 to the 10 is. No, but it is a. What is 4 to the 10 in its essence? It's a number. It's just some number. I don't know what it is, but it's a number. Okay. And so now I would like to try to make the base the same. 16 is 2 to the 4th, and 4 is 2 squared. And therefore, 4x equals 20, or x equals 5. You see how clever that is? How tricky that is? I didn't even need to know what 4 to the 10 was because I was able to make the base the same. Ready?
Don't you have just done 4 to the 2x instead of 2 to the 4x?
All right. Alternate way of working this one. Very good question. By the way, these log, and Kenneth, I'll get you a sec. These log equations that you guys look at, Freddie might work it differently than me. Aiden might work it differently than Freddie, and we all three could get the same answer, right? So let's rewrite it and attack it Freddie's way. Freddie, I think I actually like your way a little bit better. 16 is 4 squared, and those cancel out. 2x equals 10, x equals 5. Muy bueno, my friend. I know, isn't that wild? You can work these problems different ways. Ken, if you had a hand up.
But how would you think you see it? Like in your.
Oh, baby. Love it. Love it. Okay. Can I move the blue stuff out of the way? All right. Everybody good on that? Get on up there.
Yeah, 4 to 10 equals 4 to 10 is 16x.
So 4 to the 10, right? Because the can you see it approach, we start with the base, we swoop around the other side, and we finish with the argument. Now, if the argument is like there's a bunch going on, then it needs to equal that whole bunch. So 4 to the 10 equals 16 to the x, and then we're back right up there where we were a minute ago. I like the can you see it approach. It's a shortcut for the inverse property of logarithms. But in this case, Freddie spotted the fact that, hey, 16 is 4 squared, and we could go cancel those two out. Okay? And it's a really neat way. There's a third way of working it that I'll have to teach you on Thursday that involves a log property where you can move the exponent down front, and it becomes x times log base 4 of 16 equals 10. And then you would just divide both sides by log base 4 of 16, and then you get x equals 5 that way. No, it doesn't. So like if that 16 was actually like a 7, like we'd be stuck. You know what I'm saying? It's just stuff doesn't always work out nice and neat there. All right, now let's find the inverse of this exponential function. First of all, what do you know it's going to involve, just generally speaking? I heard the word log. It's going to involve logs. When you have an exponential function, you're looking for the inverse, you know it's going to involve logarithms. Now, what are our 2 steps for finding inverses?
Swap y and x.
That's the first step.
That the new one.
And solve for the new y. Good. So let's switch x and y. We got x equals 2 e to the y minus 1. Now let's solve for the new y. The new y is in the exponent, so that makes it a little bit more challenging. I could peel back the layers by dividing by 2. And what would you recommend taking of both sides at this point? We could take the natural log of the left and the natural log of the right, and those cancel, and we wind up with natural log x over 2 plus 1, because when those cancel out, that just equals y minus 1, and then we add 1 to both sides. And so there's your inverse. There's your inverse. Now, what does it also ask me to provide? So can I ask you what is the domain and range of our original function? It's the exponential function, and there's a minus 1 on the inside. So what does that minus 1 on the inside do? Shifts it which way? It shifts it minus 1 backwards. Right. Shifts it to the right. What does that 2 on the outside do? Stretches it up. So if we were going to graph out our function, let me change to black here. If we were going to graph out our function, then it would be this exponential function that looks like that.
I thought that was like fairly like a freaky thing that was gonna come in or something. Like
I don't know, dude.
I thought it was like a ghost.
All right. And then, so what are we talking about as far as his domain and range go? Domain's all real numbers. Range is greater than 0. Right? Because he's got that horizontal asymptote. Nothing was shifted up or down. So it's just got that horizontal asymptote. Now, talk to me about what the graph would look like. Its domain and range would be switched. So our inverse function, it's down here. We'll call this F inverse. Or I've got it listed here in green. Its domain would be from 0 to infinity, and its range would be all real numbers. Mitch.
Some have 2 common points with the
Oh, heck yeah, dude. You can have them infinitely many points. Here's what I'd like to do to wrap class up with. Let's go to our y equals. How to get the what? That's a squiggly 1. My pen messed up. That's 1, 1. Because actually, no, you know what it might be? I'm glad you asked that. It might not be. It might be 2, 1 after all. And therefore might not be a point. This is suspicious. I don't think this is accurate. So just for time's sake, we'll go to the graph. Here's what I'd like us to do. Let's try plotting out the original function 2 e to the power of x minus 1. So on my graphing calculator, that's my first one. It's if you hit second and then the natural log button right there. See where it's at? E to the negative or e to the power of x. And then what should my next one be? We're going to do natural log of x over 2, close parentheses, and then do what? Plus 1? Plus 1.
Flash is kind of like your 1 with
What'd you just say, Mitchell? No, you didn't. You said, bro, what the? I'm recording this and putting it on YouTube, and I'm saying that it's free for children to watch. Is that the kind of language we want to be sharing with children? What kind of weird child's going to be watching a logarithm video? I don't know. So obviously my graph is a bit jacked up because I miscued on the y-intercept. So let's fix that. I know it didn't ask us to graph. Mitchell, you should be ashamed of yourself. Watch your language. And there we go. All right, Kenneth. But yeah, think about it. It's infinitely good question that Mihalko just asked. The plus 1 shifted the whole kit and caboodle up, but because it's going infinitely down, that didn't really affect. And because it's going infinitely up, that didn't affect. The range was still all real numbers up and down. Double check your syntax. Let's see what you typed in. Did you do natural log of x over 2, close parentheses, and then plus 1? Oh, sorry. I understand what you're saying now. It's a what do you call it? Like a definition thing, like a high def, low def. You know what I'm saying? So yeah, totally. So like if you zoomed in, if you did zoom 2 and you scroll down where you think it stops, it doesn't actually stop. It's just low def. You know what I'm saying? So like you could zoom in again here and then you'll see it's still going. Yeah. Because it's asymptotic. It's asymptotic with that act. All right, listen, real quick. You guys have gotten prepped now for what? Delta math. You've got a homework 2.6 on there. By the way, I put up a little remix. If you're interested in getting the points back on, I think it was quiz 4.6. Some of y'all did not do so well on quiz 4.6. If your grade was in the cellar on that particular assessment and you would like some points back, you can try the remix and we'll see how that goes. I don't know how I'm going to treat that. I might replace the grade or I might throw some points back. IDK. That's open to anybody. I don't care. I don't know how I'm going to handle it yet. Just you if you want to try it, you try it. But this is the main thing for this week. Homework 6.2. Homework 6.2 has got 40 questions on logarithms. Okay, you've got to get that done by Thursday. No, not by Thursday. Sorry, by Monday. Monday.
That's a lot of time. Thank you.
Monday.
We
Hey,
do,
somebody already asked that like 3 times, and I said, I don't know.
I don't know about.
The one that's so I think in there, I don't think one word, so.
I gotta make up a quiz. I think it's got a quiz. Could I, you, or, you want me to do most of the quizzes? Or-
No, just do the read.